Good morning, everyone. Thank you for joining for this distinguished webinar series in AI and cybersecurity. This week, I'm honored and it's privileged to introduce Dr. Michael Schapira. His talk is titled Towards Learning-Powered Network Systems. Dr. Michael is a professor of computer science at Hebrew University. His research lies at the interface of networking and machine learning. Prior to joining Hebrew University, he was a visiting scientist at Google's NYC's Infrastructure Networking Group and a postdoctoral researcher at UC Berkeley, Yale University, and Princeton University. He is a recipient of the World Foundation's Krill Prize, faculty awards from Microsoft, Google, and Facebook, IETF and IRTF, Applied Networking Research Prizes, and the IEEE Communication Society William R. Bennett Prize. Dr. Michael, it's extremely an honor for you to having during this webinar series. I appreciate your time and effort for this, and we look forward to the talk. And now it's your time to share your screen.
Many thanks for inviting me and for hosting me. This is a pleasure. Let me just share my screen indeed. Can you see it?
Yes, good. Thank you.
Awesome. So just a few words about myself. My own research interests lie in the area of computer networking, and recently at the interface of computer networking and machine learning. And this is what I want to talk about today. I want to talk about how we can use ideas from machine learning to design better internet or network protocols in general. So stepping back for a minute, machine learning has deeply impacted a lot of areas of computer science, right? There's no way to talk about computer vision or natural language processing or other areas of computer science, many other areas, without talking about the way machine learning is integrated into these days. And yet, amazingly, it's had fairly little impact on computer systems in general, where by this I mean that the internet doesn't necessarily operate differently, nor does your operating system, because of the introduction of all these ideas and techniques from machine learning. And the big question is whether this is because of something that's inherent to these areas, or because we have not yet identified the killer apps for machine learning. So when people talk about the interface of machine learning and systems, they mean one of two things, two complementary things. One is building systems for the purpose of improving machine learning. For example, building networks that aid in making training big models faster. The other is the opposite. It's utilizing ideas and machinery from machine learning to design better systems and better network protocols. I'm mostly focused on the second, which is what I'll be talking about. And more specifically, in the past almost decade now, I've been working quite a bit on looking at two arguably most fundamental challenges in networking from a data-driven or a machine learning perspective. One is routing. Routing is the classical challenge of determining which paths traffic should be forwarded along, right? If I have a network, how do I decide which routes I'm going to use? The other is congestion control. Congestion control is another classical and super important networking task. And it basically determines who speaks when. I'll talk about this at more length in a second, but the idea is we're all sending traffic through the internet. If we don't pace ourselves, if we don't learn to play well with each other, we'll overwhelm the network. Since we don't want that to happen, but on the other hand, we want to make good use of the network, we want to efficiently utilize the bandwidth, that means that we have to apply some algorithms for determining how fast each of us should send traffic across the network. And the reason I chose these two specific tasks is not only because, again, they're two of the most classical challenges in computer networks and computer systems in general, but also because, at least from the perspective I'll be approaching these, they represent two very different algorithmic challenges. In one, there's going to be a single learning agent that's contending with a stochastic environment, and we're going to be applying ideas from statistical machine learning and stochastic optimization. In the other, we're dealing with a highly decentralized problem where we have a lot of different agents interacting, and the goal is going to be to achieve worst case guarantees. And this is going to call for a very different theoretical framework, specifically a framework that builds on ideas from online learning theory and from game theory. So let me start with the congestion control example. So a big question in general is, why do very sophisticated services like video streaming or real-time video streaming, like say voice over IP that we're interacting, using now to interact with each other, why are they facing quality of experience challenges? The most obvious example is your video rebuffering, right? This is a very unpleasant situation, which has a lot of economic effects and a lot of effects on user engagement. And we have all these services that are sending traffic across the internet experiencing bad quality of service. So in general, for example, in the US, regardless of the internet service package you get from your provider, be it 250 megabits per second to the home or higher, you're watching Amazon and Netflix content on average in HD less than 40% of the time, which is kind of astounding because you need much, much less than that to support HD video streaming. But the issue is that to reach you, all of these different services, and I'm not talking just about video streaming, I'm talking about video conferencing and cloud gaming and game downloads and all of these services that are running on top of the internet, have to reach the end device, have to reach the end user. And to do so, they have to traverse the public internet, or what we call the last mile network, which consists of a lot of different segments within the user's home, within the ISP, within the service provider itself. And the issue is that the service provider has very little control and even very little visibility into what goes on within this last mile network. So think, for example, of Netflix streaming traffic towards your home, and this traffic has to traverse, say, Comcast's network. Netflix is not in control of Comcast's network. It has very little information and very little, if any, control over how packets are handled, how data packets are handled within Comcast's network. And yet it's sending traffic into what, from its perspective, is a black box in hope that it will reach you smoothly. And this is where bad quality of experience typically manifests. It's because traffic wasn't delivered smoothly to you from the service provider. And this is exactly the challenge that internet congestion control is trying to address. So we have all these different traffic senders, traffic sources, sending traffic across the internet and essentially competing with each other over the same fairly scarce network resources. This system of pipes that is the open internet. On the other end, we have the home users. We have the end devices. And if traffic doesn't reach them smoothly and in a timely manner, they'll experience bad quality of experience. The issue is that this network pipe, first of all, cannot necessarily accommodate all of the traffic going through it. And in addition, it might be challenging even for physical reasons. Like think of a mobile network where bandwidth can be volatile and we may have different physical layer effects. So we're sending traffic through this black box in hope that it will reach the users in a smooth way. And the question is, from each of these sources' perspective, how fast should the data be transmitted? And this is a crucial question from a quality of experience perspective, because if you send traffic too slowly, this might harm performance. For instance, if a video streaming provider doesn't send traffic fast enough, you won't be able to watch the movie in HD because simply not sufficiently many bits are delivered across the network to accommodate this. On the other hand, if it sends too fast, it might overwhelm the network. This will cause data packets. This will cause data to be delayed or even lost, which will again manifest in bad quality of experience, like, for example, video rebuffering. So when we talk about internet congestion control, we talk about different sender-receiver pairs that are sending traffic across the same network that consists of different network devices like routers or switches. Packets are sent in one direction, and packet acknowledgements are sent in the other direction. So for every packet I send, I get an acknowledgement from the receiver telling me when and whether that packet has arrived. The issue is that I'm competing over this network with a lot of different other senders. And in addition, the network itself might be highly dynamic. The bandwidth along the links might change, the end-to-end latency might change, the number of competing users might change over time because someone just finished sending while another user just joined the network. Of course, a network need not necessarily be this simple. Typically, they aren't. We have much more complex network topologies in the real world. And this entire thing is decentralized. Sender one is deciding how fast to send its traffic to receiver one, with basically no knowledge regarding even the existence of the other senders and how many senders there are, let alone more detailed information like how fast they're currently sending. So we have this highly volatile environment. We have for each sender only a trickle of information about what's happening within the network, and yet each of them has to make decisions very quickly about how to adjust its sending rate in hope of, on the one hand, supporting good quality of experience, but on the other hand, reaching a good global outcome where they're not starving each other from sending traffic, and where traffic is being sent in a fair way for some definition of fair. So to give some intuition for why this can be perceived as a learning problem, the problem of determining how fast to send for every sender, think of a very simple scenario. There's a video streaming service like YouTube sending traffic towards a user. And when I say sending traffic, that means sending a lot of data packets. Traffic is segmented into packets, data traffic, and then packets are sent across the network towards the end device. Now, occasionally, packets are dropped by the network. A packet is lost. The question is, why? Why was this packet lost? One option is it was lost because the video streaming provider itself was causing congestion. It was sending way too fast. It was sending faster than the network can accommodate. And as a consequence, packets were dropped because the network capacity simply wasn't enough. However, maybe the service provider, this specific service provider, isn't at fault. Maybe the issue is that someone else was sending too fast, and this service provider's packet loss was collateral damage, right? In which case, this is actually not something due to how fast the service provider was sending. It's because of someone else the service provider was competing with over the same network bandwidth. Yet another option is that the service provider just slightly exceeded the network capacity. It wasn't really competition with others. It was just that the network has finite capacity, and at some point it was sending slightly too fast. And of course, packet loss might not even be the result of congestion. Maybe the user is mobile and was moving between base stations. Maybe there's physical layer corruption that made the network drop a packet. There's a lot of reasons for why a packet might be dropped that have nothing to do with fully consuming the network capacity. And when we talk about traditional protocol design for congestion control, traditional algorithm design, the way these algorithms operate is they hardwire control responses to packet level events like packet loss. For example, TCP, the classical congestion control protocol, whenever it experiences packet loss, it halves the transmission rate. It cuts it by half, right? But as we just saw, packet loss might be a consequence of very different things. And for each of these things, I would want to react in a very different way, right? If I'm simply sending too fast, but much too fast, I should decrease my rate by a lot, even for selfish reasons. I don't enjoy my packets being lost. But if it's someone else, there's no point in me decreasing my rate. Maybe I'm just sending at a very low rate at the moment, and I'm simply traversing a route that I'm sharing with someone sending extremely fast. There's no point in me decreasing my rate. It will lead to no social good, but it will harm me. If the only issue is that I've slightly exceeded the network capacity, I should just adjust my rate by a bit. And if the loss isn't even the result of congestion, I should even increase my rate because the network has additional bandwidth that I can consume. If all I'm doing is mapping packet level events to control responses, I'm going to always have to behave the same way every time I experience packet loss. For example, which is what's happening today for a lot of these protocols, I'm going to decrease my rate by a lot because I'm assuming that packet loss is the result of congestion and that it's a result of me causing the congestion. And both, of course, assumptions might be flawed. So let's think about this more abstractly. If I'm a traffic sender sending traffic across the internet, what's the right rate to send at? To even be able to answer this question, I need to be able to associate rates with empirical consequences. I need to have some idea of how to translate the rate at which I'm sending to a performance score. And this is something that we've been experimenting with for a while now, where the key idea is treating this as an online learning challenge, meaning I'm sending at a certain rate, and I need a function that, based on the feedback I'm getting from the other end, tells me how happy I am with the outcome. We call this the utility function. And we call the framework that I'm about to describe PCC, performance-oriented congestion control. So here's PCC in a nutshell. Suppose that I'm sending traffic to you. I'm a video cache sending a movie towards you. The way a PCC sender views this is as a sequence of micro experiments. In each experiment, I sort of test out the empirical consequences of sending at a certain rate. So I start by, say, sending at the rate of 10 megabits per second for a certain duration of time, say 10 milliseconds. And I wait for long enough for packet acknowledgements to start arriving from the other end. So I wait for long enough to get feedback from the receiver of the traffic. At that point, I can aggregate this feedback into statistics that I care about. For instance, I was sending at a rate of 10 megabits per second, but traffic only arrived at the other end at 8 megabits per second. Or while I was sending, the traffic delays increased from 20 milliseconds to 30 milliseconds, or 0.5% of my packets were lost. The next step is taking these statistics and aggregating them into a numerical value that we call the utility value. So this is, you can think of as a performance score. So in general or intuitively, this is super obvious, right? We want to be able to associate actions, in our case, sending rates, with consequences, in our case, utility values. I'll talk a bit about why this is easier said than done, and you can ignore this formula for now. But there's another component. And the second component is, suppose that I tested out the empirical consequences of sending at certain rates. I sent at a rate of R1, and after some time concluded that the utility value is U1. Then I send at a different rate, say R2. After a while, I conclude that the utility value is U2. What should my next rate be? And this is where ideas and techniques from online learning theory are very helpful. So in online learning theory, we have a decision maker, in our case, the traffic source, that has different strategies, in our case, the sending rates, and is confronting a chaotic, possibly even adversarial environment, in our case, the last mile network, this black box that we're injecting traffic into. And the decision maker has to constantly decide between actions, has to constantly adjust its sending rate in hope of getting good performance. So in PCC, when we're designing PCC, the key challenges are how to figure out what utility functions to use and which online algorithms to use to decide on what the rate next should be, the next rate should be based on the previous rate experiments. And diving a bit deeper, if we want consistently high performance, we need to choose utility functions that achieve two different properties. One is the utility function should be such that its objectives are aligned with what the service running on top actually wants. For instance, if we're video conferencing, latency is super crucial. I don't want to reach a situation where packets are lost within in-network queues and have to wait their turn to be sent across the network. I want to make good use of the network without overshooting. On the other hand, if this is video on demand, it's fine if the video starts half a second late, but then I want to be able to send a lot of data because I want to send the traffic in HD or maybe even 4K. So different services or different applications want different things from the network. But the other aspect of choosing a utility function correctly is that when we're choosing the utility function, we're also determining what the equilibrium is going to be when different senders interact. And if we want, for example, different senders to allocate the bandwidth, to share the bandwidth fairly, that means that we need to choose the utility functions in a very careful way, because every sender is optimizing its own utility function with essentially no knowledge of the other sender's existence. And yet we want them to play well with each other. The rate control algorithm is also crucial to choose correctly because we want to be able to quickly converge to an equilibrium when we have multiple senders competing with each other. But also, if the network drastically changes, we want to react very quickly to that. So in PCC Vivace, which was one of the protocols that we've presented for accomplishing this, we were able to harness the theory of online learning for achieving exactly this. So the idea was being able to decide on a utility function that satisfies certain mathematical properties that we care about, namely is strictly concave. And just to say a word about what you're seeing here on the left, what you're seeing is a utility function that basically balances different performance objectives. I want to be able to send traffic quickly, but I want to be penalized for traffic being delayed or lost because of me sending traffic too quickly. So what you see here is basically a utility function that's configurable and enables you to balance or weigh these different performance objectives in different ways. The online learning algorithm is simply running gradient ascent on this utility function. So if I'm a sender, I send at a certain rate. I learn what my utility value is, but I do more than that. I also try to understand in which direction and to what extent I should change my rate to improve performance. And this I do by learning what the gradient is at my current location, at the current rate. Once I know this, I move in the direction of the gradient and continue this process. And what I want you to take from this is that one way to view what we're doing here is as engineering a non-cooperative game, where we have these different senders, they're sending traffic through the same network. Each one is oblivious to the existence of the other senders, with the exception of what it perceives from the network. Its packets being lost, its packets being delayed. And yet we want to be able to choose both the performance scores, the utility functions of these different senders that we can think of as players in a game, and the algorithm they're using to switch between strategies, sending rates in our case, in a way that's both beneficial to the individual sender. That is, the individual sender gets good performance, even when not assuming anything about the network it's sending its traffic through, but also, if it is competing against other senders using our protocol, you're guaranteed to converge to an equilibrium point where traffic is being fairly allocated between these different senders. And let me linger a bit on these two things. We want local guarantees. We want the services to enjoy good quality of experience, but we also want a global guarantee. We want convergence to a fair outcome. So this has been proven in battle in the sense that what you see here are results from live deployment at a large video streaming provider in the US. This is for live streaming content and from multiple locations, New York, Seattle, Dallas, and others. And this is based on millions of hours of real video streaming. What you see on the left-hand side is the reduction from the user's perspective in the time spent rebuffering. So the rebuffering ratio is the fraction of time your video spent rebuffering out of the total time you were watching the video. What you see on the right-hand side is the improvement in video bitrate, in the resolution. So in particular, we were able to support 34% more sessions in HD than that provider was able to support before. But remember that getting good performance is not enough. We also want to be fair. So just to give you an intuition for why this is accomplished, what you see at the bottom is a very simple experiment where you have a single link and different senders are starting to use this link at different times. First, we only have the red sender. So the red sender is fully utilizing the link capacity. But after a while, the green sender starts sending traffic. At this point, we want them to share the bandwidth fairly, and indeed they do, right? So you can see that the red sender decreases its rate and the green sender increases its rate. And this is precisely the provable guarantee of reaching a fair equilibrium if you design the utility functions correctly and if you choose the right online learning algorithm. Now the blue sender enters, and now they start equally sharing the link. So each one gets a third. When the pink sender enters, it becomes a fourth, right? And then as senders stop sending, again sequentially, the share between the surviving senders is readjusted to match the fair share. At the top, by the way, you're seeing TCP, which is still the de facto protocol used for most video streaming today. So you can tell that, by the way, on average, it might be sending at the fair share, but there's a lot of fluctuations and a lot of jitter. So since presenting this online learning framework for congestion control and this game theoretic approach to congestion control, we've been looking at various different angles for enhancing this framework. In particular, using deep reinforcement learning to replace the algorithm I just mentioned, and also sending traffic along multiple paths and not a single path. What I want to talk about very briefly, because I think it illustrates the expressive power of this theoretical framework, is application-oriented congestion control. So we have very different types of internet traffic, right? There's game downloads, there's video streaming, there's software updates, and so on and so forth, cloud storage replication, and so on. But very broadly speaking, we can divide them into two sets, into two classes of traffic. Time-sensitive traffic versus, maybe not non-time sensitive, but much less time-sensitive traffic. Think of video conferencing, where it's crucial the traffic arrives at the other end in a timely manner, versus a software download, where it's perfectly fine if it stops for 2 minutes, as long as eventually, right, in the near future, it's completely downloaded. Now, think of Alice and Bob. Bob is downloading a software update, say, or is replicating its storage, whereas Alice is watching a movie. If all of these connections are treated the same way, they're going to equally share bandwidth. But this might be horrible, because for Alice, the consequences are very dire. If there's not enough bandwidth to support video streaming, she's going to experience bad quality of experience, like video rebuffering. On the other hand, for Bob, it's not too bad, right? And Bob could actually have waited, right? And an even more obvious scenario is if Alice herself is downloading a software update while watching a movie Obviously, Alice prefers for the movie to be sent in HD or for the video conference to not experience stalls than for the software update to be delivered. So what's our goal? Our goal is to support two modes for congestion control. One that we call the primary mode for applications that are time sensitive, like online video streaming, and the other that we call a scavenger mode that should take over bandwidth only when it's not competing with primary connections, with primary flows. So what do we want? We want scavenger flows like Bob's to yield to primary flows like Alice's. In addition, if there's only primary flows or only scavenger flows, we want to make sure that they all achieve high performance, right? If both Alice and Bob are downloading a software update, I want to make sure that they are fully utilizing the available bandwidth and sharing the bandwidth equally between them. And the reason that I'm mentioning this is because here's one way of doing this. If you recall, we can think of PCC as basically engineering a non-cooperative game. So one way of doing this is by simply selecting the appropriate utility functions for Alice and for Bob so that they optimize different things, but that in equilibrium, I get exactly the behavior I want. That if all flows are primary, they fully utilize the bandwidth and equally share them. Same goes for the case that all flows are scavenger flows. But if I have a mixture of scavenger flows and primary flows, the scavenger flows will yield. They will basically stop sending or send very slowly to make room for the primary flows. There's, of course, a lot of technical details. You can look at the paper, but I think it goes to show that there's a lot of expressive power here in this theoretical framework. So the next application domain that I want to talk about is learning-driven routing. And here, think of a very different context. So we have hyperscalers like Microsoft and Google and Netflix and Facebook that are serving customers from data centers all around the world. In this figure represented by the dots, by the nodes. And these hyperscalers invest huge effort and also billions of dollars on provisioning and managing backbone networks, private backbone networks that interconnect their data centers. Now, to fully utilize these networks, they have to decide on good flow allocations. They have to optimize routing within these networks. This is known as traffic engineering in the networking literature. So in the classic traffic engineering model, and I'm sure this will resonate with some of you because it's basically an extension of max flow, min cut that we learn in algorithms courses. The input consists of several elements. One is the network topology that you can think of as a direct capacitated graph. The other is tunnels. So these are specific paths that are part of the input, and the traffic can only traverse these specific paths. So for example, between 1 and 2, we have the red tunnel and the blue tunnel. And similarly, we have predetermined tunnels for each communicating pair. And then there's the demand matrix. The demand matrix specifies how much each sender wants to send to each receiver. So the ijth entry in the demand matrix is how much traffic I wants to send to j. And then we have an optimization objective, like, for example, maximizing the flow across the network. And what we want to do is to identify the optimal TE configuration with respect to this objective, where by TE configuration, I mean the fraction of traffic sent by each source across each of its tunnels towards the destination. For example, one possible choice of splitting ratios for one would be 32% of one's traffic is sent directly to 2, whereas 68% has to traverse the blue tunnel. And similarly, in a global TE configuration, we'll have traffic splitting ratios across all tunnels for all source destination pairs. And here's where machine learning comes into the picture. We have so far assumed that we know the demand matrix. We know how much each source wants to send to each and every receiver. But how do we know them? Typically in practice, we don't. We have to commit to a routing configuration, to a traffic engineering configuration, before we actually see how much each source is going to send. The way this is handled in practice is predicting the upcoming demands. So for instance, we'll have some predictor that examines the demand matrices from, say, the last hour, and we'll use this information to predict what the traffic demands are going to look like in the next 5 minutes. Once it has this demand matrix, it will feed it into an LP solver, because typically flow optimization can be done by solving a linear program. So it will feed it into a linear program solver, which will then output traffic splitting ratios. And here's why this is problematic. So what you see here is traffic from Microsoft's backbone network. And this is between the pair of data centers that sent the most traffic towards one another across an entire week. So if you look at the orange plot, what you see here is how much traffic was sent at 5-minute granularity across the entire week. Notice the obvious temporal pattern. All weekdays look pretty much the same. Both weekend days look pretty much the same. Right? And there's a very clear pattern here. And if you look at the bottom, what the bottom figure shows in blue is the variance across different weeks. And as you can see, the variance is very low. So this means that traffic between Microsoft's data centers, where it's essentially Microsoft sending traffic to Microsoft, is extremely predictable. What you see now is similar results, but for a different type of traffic. This is customer-facing traffic. This is Microsoft sending traffic towards external networks. Think voice over IP or search or chat GPT. So now, not surprisingly, traffic is much more volatile because it's triggered by external requests, and the variability across weeks is very, very high. And indeed, this traffic is extremely unpredictable. And if we revisit the demand prediction approach, there's two drawbacks here. One is that if we feed highly inaccurate demand matrices into the optimization engine, into the LP solver, naturally we're going to get bad outcomes because it's garbage in or garbage out. The second is solving a linear program on a very big network is itself extremely time consuming. So what we proposed, which we call DOTE, Direct Optimization for Traffic Engineering, is replacing this flow with learning a model that directly maps the recent history of demand matrices into a T configuration. So it doesn't go through this step of explicitly predicting the upcoming demands and explicitly feeding them into an LP solver. It uses a deep neural network to map, say, the 12 demands from the recent hour at 5-minute granularity into the traffic engineering configuration that I will use in the next 5 minutes. And this addresses both drawbacks because now the learning objective is precisely the end-to-end optimization objective. It's precisely what the system designer wants to optimize. Also, because we're using DNN inference instead of solving an LP, this can be done much more quickly. So for both demand prediction-based routing and DOTE, we have to train a learning model offline. But we're training the model to learn different things. And so the output is different and the performance metric is different. In demand prediction, like I said, we're trying to figure out what the upcoming demands are going to be. In DOTE, we're trying to learn what traffic engineering configuration, what global routing outcome to use to get good performance. And this is why the performance metric for demand prediction is how close I was to the actual demands, whereas for DOTE, it's how good I fared with respect to the traffic engineering objective that I cared about. For instance, sending as much traffic through the network. So I want to give you some intuition for why this works. So think of a very simple network. We have two source nodes, A and B. They both want to send traffic to node D and node D only, and they can each send traffic along one of two tunnels, the direct path, say AD, and the indirect path through C, for example, ACD. Same goes for B. B can only use the tunnel BD or BCD. All link capacities in this example are 1. Occasionally, so say every 5 minutes, the system has to decide on traffic splitting ratios across the tunnels for each of these two source nodes. The problem is that the system has no a priori knowledge of what the traffic demands are going to be. Now let's assume that A and B's traffic demands are actually drawn from some fixed probability distribution. With probability half, A wants to send 5/3 and B wants to send 5/6. With probability half, A wants to send 5/6 and B wants to send 5/3. Importantly, the T system not only doesn't know which of these will be realized, it doesn't know the distribution either. Now let's assume that our goal is to minimize the maximum link utilization. This is a classical objective in multi-commodity flow, in flow optimization, where we want to minimize across all links the maximum of how much traffic is sent across the link divided by the link's capacity. And here's the crucial observation. If we look at the expected maximum link utilization as a function of A and B splitting ratios, it's convex. It has this nice structure. And this nice structure means that if we were to apply gradient descent to the expected maximum link utilization, regardless of which splitting ratios we start with, we'll eventually reach this red point, which corresponds to the optimal traffic splitting ratios in this case, sending 0.6 of the traffic along the direct path and 0.4 along the indirect path. But here's the problem. How can we estimate the gradient of this function we just saw at each point if we don't know the distribution over demands? If we don't know the distribution over demands, that also means that we don't know what the function looks like. And to achieve this, we can rely on two observations. One observation is that for each realized demand combination, suppose that A actually wanted to send 5/3 and B actually wanted to send 5/6, for each one of these realized demand combinations, we actually know exactly how the maximum link utilization is going to behave. And we can see this in this formula, which is basically the maximum between the load on the link AD, the load on the link CD, and the load on the link BD. Because we know this, we can also explicitly derive the gradient of the maximum link utilization, again, with respect to this specific demand realization. The second observation is that we average over sufficiently many past observed demand realizations, we can closely approximate the expected maximum link utilization. So if we want to estimate the gradient of the maximum link utilization for a specific traffic engineering configuration Xi, we only need to examine past demand realizations, derive for each one the gradient of the maximum link utilization at Xi, and then average over these. And if we examine sufficiently many such demand realizations, we'll closely approximate the gradient. So this was a toy example, really, but the solution can be extended to handle temporal patterns in traffic, where we're not constantly drawing the traffic matrices from the same probability distribution, but where we have temporal patterns as we saw in real traffic. And to this end, we need to use a deep neural network. It can also generalize to arbitrary network topologies and traffic choices. And maybe most importantly, it can also generalize to other flow objectives like maximizing the total flow across the network, or maximizing what's known as concurrent flow, which is another classical flow optimization objective. The proof here is much more subtle, and this is actually where most of the technical depth lies, because convexity no longer holds. So you really need to identify other key properties of these functions that are of value. So to evaluate this, we proved theoretically that in well-studied theoretical models, we actually converge to the optimal routing configurations. And we also ran empirical analysis using huge volumes of traffic traces from actual operational networks. What you see here are results for maximum link utilization, where the results are for 4 different operational networks, 2 of which are Microsoft's own backbone networks. And low here is good. Dot in red is us, the green is demand prediction, and the rest are other traffic engineering baselines. 1 is the optimum. And interestingly, Dot almost matches the optimum achieved by an omniscient oracle with perfect information about future traffic demands. So I'm going to skip some of these evaluation results because I want to use the last few minutes I have just to talk about some of the things I'm not going to talk about at length. But what we just saw is a system that uses deep learning to tackle a classical traffic engineering, a classical networking challenge. But the problem with using deep learning engineering for a task that you crucially care about is that to a large extent, decision-making by deep neural networks is still obscure and it's hard to reason about. And in particular, if your network is trained in one environment, your DNN is trained in one environment, but is applied to a very different environment. For example, suppose that for whatever reason, a failure that I didn't anticipate or some new service being launched, the traffic pattern across my network changes drastically. The algorithm might fail miserably in addressing this. And this is a well-known problem, bad generalization of the learned policy with respect to new or unforeseen inputs. So one thing that I've been working a lot on these past few years, and I know this talk is at the conjunction of AI and cybersecurity, and I think that this is where it relates to cybersecurity, because I'm looking at this from the perspective of I don't want my system to perform badly, even for benign reasons. Right? Like I said, a network failure, a new services being launched. But these same techniques are also useful for reasoning about the safety of any deep learning-based system being deployed in the real world. So there's different approaches one could take. One is robustifying the training process itself. For example, by introducing challenging scenarios into the training process. This is a well-known technique, but when you're trying to use it in computer systems context, it requires some care. The other is formally verifying deep neural networks, meaning when we're simply deploying traditional software, we have acceptance tests. But when we're deploying a deep learning-based system, what's the analog of that? Shouldn't we have some sanity tests that we can actually validate that hold regardless of what inputs the system will encounter? This is where formal verification is extremely handy. And lastly, and this I think is a very interesting direction conceptually, when does the system know that it's no longer making reliable decisions? Can it learn this online and switch to a safe policy? Like, for example, some manual control rule. And this is not obvious because it's not just a matter of figuring out that the environment you're operating with, it no longer matches your training environment. It might also be the case that it doesn't match the training environment, but you're actually making good decisions, right? So what you actually care about is figuring out when you're making bad decisions. But this is very hard to tell online because maybe the reason you're experiencing bad performance isn't that you're doing something wrong. It's just that the environment currently is extremely challenging. So just to conclude, I think that learning-driven networking, and maybe even more broadly, learning-driven computer systems are still in their infancy, but I think that there's many fascinating open questions, and time will tell whether we're now discovering the killer apps for machine learning in this world, or whether there's some obstacles that we have yet to remove. But I think that this is super interesting. So thank you very much.
Thank you so much, Dr. Michael. I think fascinating talk, and especially the last few slides were even, I'm sure a lot of graduate students appreciate the open research problems that you actually mentioned. So I love that last bullet that you had about online defaulting, and in terms of fail-safe mode for alternative solutions. I think let's see for Q&A sessions. Nirup, could you put Dr. Jun Lu on as a panel so he can ask the question? It looks like we have.
So I have already been unmuted. Okay, so thank you. Thank you for the talk. Yeah, so I also somehow noticed that the learning machine learning based networking is start to gain its momentum. And so after reading into your presentation, I somehow have a question about the result that you have presented covered around the slides 20 or something, and that seems to me is a more pretty much static, even though just whenever you just replay of the different sessions of the TCP the TCP experiment, even though the changes will be there, however mostly the statistical patterns, or because we are using the computers, okay, to simulate that, each different sessions of the experiment pretty much remains the same, and so my question is that it seems to me that your method has did a good job in handling the static traffic, relatively static traffic cases. What will happen if somehow we purposely just insert a disturber there, just trying to somehow just change the delays, just there definitely a way to change of those things. In that case, whenever the disturber gets inserted, how do you think that your method will continue to work with that disturber?
So thank you for this question. I think that you're touching upon a really important point, because I share your skepticism about a lot of the statistical machine learning based approaches to congestion control. So for example, I myself have worked on applying deep reinforcement learning to congestion control. And I think it's an interesting direction, but I think that there's a lot of obstacles that are problematic in the real world. And one of which, maybe one of the biggest ones is what you just said, right? There's so many different network environments that can be so dynamic that I may encounter that it's really hard to train in a way to train the model to learn a policy that's sufficiently robust. The reason that I presented this specific scheme is because it draws, and this is what you see in this slide, it draws from a very different body of literature, which is multi-armed bandit theory. So here, the assumption is that you're contending with an adversarial environment, and you're trying to attain worst case guarantees. So in your example, this is an online learning scheme. In your example, if there's a disturbance to the system, I can give you provable guarantees that after sufficient time, you're going to get good performance in the sense that there's no static sending rate that would have been better for you in hindsight. This is what's known in this literature as regret minimization.
I see.
Not only that, but if there's multiple senders, they're guaranteed to converge to an equilibrium. And the reason that I'm advocating this framework, for example, in this talk, is precisely because of what you said. I think the issue with congestion control, unlike the routing example, is that there's so little knowledge about who you're competing with. And you know so little about how the environment might change. And there's such a daunting breadth of possible environments that trying to train offline and then just hope for the best online, right, is a very risky choice.
Okay, I see. So is it fair to say that, your method actually targeting for the scenario at the, the backbone, at the backbone level, yeah, your method really make a lot of sense. But however, whenever the same method gets moved, close to the downlinks, close to the, the end users, then, things probably may look different. And also I have a related question. The related question is that how, whenever you're trying to train your model, so, in that case, we want to have, the good of the, distinction or the good, or say to be able to differentiate, among so many different situations in order to be able to know that, in what region that, we are talking about. So in your method, I doubt that, the distinctions will not be able to well addressed, means there will have a lot of overlaps. So from the backbone ISP perspective, those overlaps, may be fine, okay. But whenever we move to the downlinks and the poor distinct, if we cannot, well distinguish, enoughly for the different situations, then pretty much I do not see that, we can be able to do a good control in that case, or gaining a good utilization.
I think that we're once again in agreement in the sense that one of the things I've learned was that the hardest part of tackling these questions is identifying the right hammer. And there's so many nuances of hammers, right? So the reason that when we talk about what you call downlinks, right? I wouldn't advocate using this specific routing scheme, DOT, for example, for choosing internet routes. I think it's most appropriate for private backbone networks precisely because the problems you mentioned about volatility and uncertainty don't arise. This is a controlled network where it's the same entity sending traffic towards the same entity. In the congestion control case, the reason I avoided statistical machine learning is precisely this. The reason I opted with something that gives you provable worst case guarantees is because I want to be extremely robust, is because I want provable guarantees. So I think that one of the things that we're still figuring out in our community is which flavors of machine learning are appropriate. And there's a lot of work to do here on figuring out what the right nuance is for each and every one of these environments. Because take routing or congestion control. It wasn't just routing and congestion control. It was routing within a single organization and congestion control across the public internet. If you were to even change the context of one of these, say routing across the public internet, congestion control within a data center, congestion control between data centers, this would call for very different solutions.
I see. Yeah, I hear you. Thank you so much for your explanation. And I also hear about, just, one kind of the opinion saying that, so as the computer network continues to evolve, there is one view saying that, for, as more and more application level of the multiplexing will happen even more, then based on the central limit theorem, no matter how dynamic of the individual link varies, when the multiplication will be more significant enough, then in the end, pretty much we will be able to see rather clear statistical patterns at the backbone level, or whenever we move down to the layers, then the traffic pattern will become more and more fixed in terms of the statistical patterns. So do you agree of that opinion? Or
I think that once again, I agree with it at some level, right? Meaning if you're looking at things at fairly long time scales,
Mhm.
right, and at a lot of traffic, right, then the law of large numbers, right, works, and you can deduce all sorts of things. But there's so much noise, right? The routes are changing underneath. You're competing with services that are using different congestion algorithms than yours, and that whose traffic is constantly changing. New services are being deployed, links fail. So I think it depends on the time granularity. This is why, for instance, if you're making decisions, say you're Microsoft and you want to make decisions about how much capacity should I augment my network with, maybe you can look at months of data, maybe even years of data, and there's certainly a pattern, right? In the congestion control example I gave, or tens of milliseconds, right? It's going to be very hard to distill a pattern from that. So I think it really depends on the feedback loop that we're talking about in the specific environment. For maybe global decisions at long time scales, right? I think you might be right, but for a lot of these challenges, there's going to be a lot of dynamism and a lot of surprises.
Great questions, and I think the more problems to attack. I think in the interest of time, I had one question I want to ask anyway. Maybe that will be the last question, but I think we can close with that question. You talked about this utilization function rate, which is going to be the key in controlling this flow. But you already answered that question in some sense, depending on whether you're looking at this network at within an organization, how this type of thing. But do you see, in terms of some kind of using machine learning to determine the utility function or dynamic utility function, a data-driven based approach to automate the process of, I don't know. I'm just curious to see, is that something you're working already, or I'm sure that.
So I'd say working is an overstatement, because I'm struggling with mostly, but I fully agree. So one of the issues here is that the utility function is, there's a lot of underlying trade-offs that I didn't go into. But for example, it's not as straightforward as saying, and I sort of hand waved this, but it's not as straightforward as saying, if I want to experience low latency, I should just make my utility function penalize for increases in latency. It's not that straightforward, because, for instance, if I'm competing against senders that don't care about latency, what will end up happening is just me decreasing my rate and them taking over the entire link. So I'll both experience high latency and not send traffic across the link. So there's certainly room for this longer feedback loop for changing the utility function with respect to what the service actually cares about. And I think this is a very interesting direction, and this should probably be done at a much longer time scale, going back to what June said before, right? Because now you want to make sure that what these changes actually reflect a lot of data that you've gathered about the network you're operating in.
Great. Thank you so much for your insight. It's a great presentation, and we'll conclude this webinar with this now, and then we will we'll send you a nice plaque and certificate signed by our dean, and a token of appreciation. And thank you so much, Dr. Michael. We look forward to working with you as we see some opportunities come. Thank you so much.
Many thanks for inviting me. This has been a pleasure.